So I went through this Markov property in details for two reasons. Once there was a question about it. There were actually two questions about it in the email. And also I want you to get used to use of Markov property very well because it will be used over and over again in this entire course. Now there is actually an alternative to use of Markov property and directly do it from the equation MC, remember, that we used to define a Markov chain. I'll also do that and show you this equality here. This equality I'll show using MC. So remember, if you take, we have to take KL in a set of positive integers and then state as needed. So the first k minus 1 of these i's should not be equal to I, and then the last one, kth one, should be equal to I. Similarly, for the j's, first L minus 1 should not be equal to I, and the JL should be equal to I. And then we already showed that this quantity, this is the numerator of star, is actually equal to this probability. Now I have color coded them, and there is a reason why. So this huge joint probability starting from I. Now let's use MC, which is the definition of a Markov chain. So this is the Markov chain starting from I. So initial distribution is delta I, and transition matrix Pij. So therefore, this huge joint probability would be given by this product here. Yes, so from I you go to I1, then from I1 you go to I2, and so on. You go to Ik minus 1, then from Ik minus 1 you go to I. Then from I you go to J1, then from J1 you go to J2, all the way up to JL minus 1, and then from JL minus 1 you go to I. You have this huge joint probability. This part is coming from this red part, this red numbers here, the red part here is coming from this red part of the event, and this blue part is here, quantity is coming from this blue part of the event here. Now interestingly, this would be equal to this probability times this probability, what we have to show. The red probabilities, the product of these red probabilities is equal to the joint probability x1 equal to I1 all the way up to xk minus 1 equal to Ik minus 1 times xk equal to I. And xk equal to I. Okay. So this joint product, this is exactly from MC again. Also, if you just consider it on the blue part, that's just this probability, this joint probability. Starting from I, you go to J1, then J2, all the way up to JL minus 1, and finally return to I. So this is just this blue probability. So therefore, this shows the equality of this with this using MC. So we are using the definition of Markov chain that we took for this course, as opposed to the Markov property itself. Okay, and we know they are equivalent, so it doesn't matter. But this is, in some sense, more neat. It's more direct. So you should get used to both methods, and that's why I gave you both methods of proving. Okay. So now, I'll first give you an exercise. So using MC, or you can also use Markov property, you show the following. You show that for all positive integers, KL, and for all states I1 up to IL in S, the joint probability of the first return time equal to K, and then right after that, the Markov chain is at I1, I2, all the way up to IL. So after the first return time, right after that it's at I1. After 2 steps it's at I2, all the way up to, after L steps it's at IL. This joint probability is given by the product of the marginal probabilities, namely the probability starting from I, the first return time is equal to K, times the product starting from I, after the first return, strictly after the first return, right after the first return, the Markov chain is at I1, then it's at I2, and so on, all the way up to IL. So in other words, what I'm asking you to prove here is on the event that the first return time is finite, the first return time is independent of whatever happens after the first return time. So this is essentially whatever happens, this happens after the first return time. So the first return time is independent of whatever happens after the first return time. But in order for that to make sense, the first return time should be finite. Otherwise, nothing happens after first return time. So therefore, on the event that the first return time is finite, whatever happens after first return time is completely independent of the first return time. Again, this is just a manifestation of Markov property, and I want you to use MC, the equation MC, to prove this. Okay? So the definition of Markov chain to prove this result. Okay, so let's go back to the proof of dissection principle. I have been very slow, and because it's a long proof, and what I have told you is that it's enough to do it for this kind of states. So I1 to ik minus 1 and j1 to jl minus 1 not equal to I, and ik and jl equal to I. And in this situation, what we have proved is that under Pi, the joint probability of xi1, xi2 taking values, these two values, along with first and second return time is finite. This becomes a product of xi1 taking this value and first return time is finite, and xi1 taking this value now and the first return time is finite. So this is something we have achieved also, proved already. Okay, last class itself we proved this. And from there we also proved that under Pi, the joint probability of tau I and tau 2 both finite. So tau I1 and tau I2, the first two return times are both finite. It's just a product of the marginal probability of the first return time finite square. Instead of product, I would say it's a square of, so square of the first return time finite, starting from I. Now again, as I would say, in all of these statements, this kind of events are redundant, because in the first one, for example, the first return time is equal to k because of the choice of the states. Okay. And the second return time is actually exactly equal to L. Therefore, in particular, they're finite already. So therefore, these two events were actually redundant. So this, we could have not written these things, but we decided to write them. Similarly, for the second quantity here, tau I1 is already L. Here, tau I1 is already, in this case, it's already K. In this case, it's already L. So they are redundant. But let's keep them. If we keep them, what we will achieve is that we can divide this red equation by the blue equation here. If you divide the red equation by the blue equation, what you would get in the left-hand side, you would just get, instead of Pi, you will have Pi hash. This is because if you divide by this quantity here, you're essentially conditioning on this event. And that's precisely Pi hash. So under Pi hash, the joint probability of xi1 and xi2 is what you would get from the left-hand side. What about the right-hand side? In the right-hand side, you will get, this will become a conditional probability and this will become a conditional probability, because you have square of this, you're dividing by that, you divide one here and one here, so you'll get conditional probability here and conditional probability here. So dividing the red equation by the blue equation, you will get this violet equation, which is just a statement about conditional probabilities. And this is the reason why we kept on keeping these redundant events here, so that we can finally get to the conditional probabilities. So let's summarize what we have achieved. So we have achieved that for states on which we have to prove the things. So other than that, the start is trivial. Okay, so basically you take I1 to ik minus 1 and j1 to jl minus 1 all not equal to I, and ik and jl equal to I. Then under Pi hash, this probability is equal to the product of these conditional probabilities, which would be equal to pi hash of psi1 taking this value and pi hash of psi2 taking this value, and complete the proof of star. Except that only problem is in pi hash we have a double conditioning. We have a conditioning with respect to the intersection of the first two return times finite, whereas this statement is about one being finite. So we actually have to, in order to show that this is equal to this, we actually have to prove that this pi hash is given by this quantity here. If you can show that this is equal to this, then by a similar logic, so basically I am showing this is equal to this. Okay. If I can show that, then by a similar logic, this guy would be equal to this guy. And therefore this product would be equal to this product. And this will complete the proof of star. Star was proving this is equal to this, remember? Okay. So therefore, we just have to prove this claim. And in the claim, what is the difficulty? The difficulty is that here you have conditioning with respect to both first and second return time finite. Here we are getting rid of one of the conditions. We are second return time finite is sort of not needed, is what we are saying. But we'll have to show it. So essentially, the proof of dissection principle will be complete, provided we'll prove the claim.